Hey, here's chapter 15, video number 2. I'm sorry about the abrupt ending of the last video. My phone is driving me nuts. It just all of a sudden cuts me off if I reach like 30 minutes. That's why I've been trying to limit these to 30 minutes so I don't get cut off. But I'm hoping to finish everything in this video. If not, then there'll be another video just wrapping things up here. I just have talk about esters a little more and the compounds called amines. But you're probably tired of looking at my hands. When I watch these videos, I see I'm trying to keep my hands presentable. They got some ink marks on them and things like that. But I figured this is the best way to present this material close up instead of me standing at a board in front of you, because I think you can see everything clearly here. But I just found this, I'm using this hand lotion here, and I looked on the label. I said, well, I can show you guys. I just show you the ingredient label of the hand lotion. You can see a lot of the compounds are similar, like names of stuff that we've been discussing. For instance, obviously water is the #1 ingredient, but if you see here, it's got glycerin in it, which is is a byproduct of when you break down soap. When you make soap, you get glycerin as a byproduct. It's got stearic acid, which is a long-chain fatty acid, sort of related to soap. Palmitic acid is a long-chain fatty acid that's used to make soap. What else did I notice along here? It's got sodium hydroxide in it, probably for pH balancing. It's got panthenol, which I don't know, I guess it's a long-chain alcohol. It's got limonene, which is an alkene, double bond. Limonene is the main component that makes lemons smell like lemons and oranges smell like oranges. Hexylcinnamol, I'm presuming, is a aldehyde. Benzyl salicylate, there is an ester. Geraniol, eugenol, those are alcohols. So you can see, now that you've had a little bit of organic chemistry discussion, you can kind of understand some of these food labels and hand lotion labels. A knowledge of chemistry is definitely helpful in our everyday lives. So anyway, what I was talking about last video when it abruptly ended was talking about some of the characteristics of esters, and they generally smell well. They're used in perfumes and food flavorings and cosmetics. They're used, as you know, as building blocks of plastics and polymers, polyester. They're used to make surfactants, including soaps. Esters are found in an important class of biomolecules, including pheromones and fatty acids of glycerol. Phosphoesters are found in the backbone of DNA. Again, that is phosphoesters are like, instead of carbon, it's phosphorus. And they're extremely important in ATP, it's called. It's the energy molecule that is used in our bodies to convert food into energy. Extremely complicated stuff. But let's just talk a little bit about how you make esters. There's a very famous reaction invented around 1895 by Emil Fischer, and it's still used today. We still run it in laboratories to teach students about how to make esters, and we can give students different acids and different alcohols, and they can make, one student can make something that smells like oranges, and another student can make something that smells like apples, and another student can make something that smells like nail polish remover. All sorts of smells can be generated from esters, and generally pleasant smelling stuff. But an acid, the classic way to make an ester is to take a carboxylic acid and an alcohol, and when you combine them, a water molecule is lost, and you get an ester. So this is if you ever go into this sort of study or chemistry more, you'll see that water is spit out of a lot of organic reactions as a product. For obvious reasons, it's very stable, and it makes the energy, the thermodynamics of the equation very favorable in the left to right direction, so we produce product. That's what we want. I write this as an equilibrium because the energy of esters and waters is very similar to the energy of the alcohol and acid that make it. So When chemical companies make esters on a very large scale, they generally will boil them off as they make them. And Shatley's principle, as you know, says that if you remove a product from an equilibrium, the equilibrium is going to shift in the forward direction to compensate for the removal of the product. So that's one way we can trick the molecules into making more of the product, is if we remove a volatile product. Esters are pretty volatile things. They generally have boiling points less than 100 degrees. But notice it's very important to understand that the oxygen that's part of the ester, this singly bonded oxygen I wrote in red here, comes from the alcohol. And the acid part that becomes part of the ester, the only part that it loses, the OH, that's part of the carboxylic acid. So how did they figure that out? Well, what they did was pretty clever. They actually labeled oxygen with a radioactive isotope, and they were able to follow the radioactivity through the reaction, and they found, they were able to figure this out, that the oxygen of the alcohol actually became part of the ester itself. The oxygen that was part of the acid was spit out as part of the water. Very famous reaction, very useful, pretty simple to do. You just mix pretty much equimolar amounts of carboxylic acid and ester, or I'm sorry, and water and alcohol, sorry. And it needs an acid catalyst. So we usually use sulfuric acid as a catalyst to kind of kickstart the whole reaction, and then you just essentially just stir it for about an hour, and you get an ester and water, and it's pretty easy to purify. And you can make a whole variety of esters depending on the R groups that you have, whether it's 1, 2, 3, 10 carbons long over here, or various number of carbons over here, or an aromatic ring. You can make all sorts of different smelling esters and with different applications. So as I've done with all the other functional groups, let's talk about how you name these things. So it's a little bit more complicated than the other functional groups, but nothing I know you can't handle. So how do we do it? Let me just give you some examples. Here is an ester. You know it's an ester because, again, you see what looks like the carboxyl group, but on both sides it's got carbon. So you know it's an ester. This part comes from the acid, so it's 2 carbons long. So 2-carbon acid is acetic acid, and that becomes we change the ending of the acid name to ATE. And then this part comes from the alcohol. Well, a 2-carbon alcohol is ethyl alcohol. So when we name an ester, we always name the part that comes from the alcohol first. And in this case, it came from ethyl alcohol, so we call it ethyl. And then a second word, we name the acid part acetate. But there's another name for this particular molecule because it's got 2 carbons in it. The other name for this is ethanoic acid because it's got 2 carbons based on the hydrocarbon, as you know, ethane. So we can call it this, ethyl ethanoate. And this is the IUPAC name. This is the common name. This is the chemical, if you've ever used nail polish remover, that's the smell. That very characteristic nail polish remover smell is the compound ethyl acetate. And here is the line drawing of it. CH3, C double bond O, CH2, CH3. A little more complicated example of an ester is taking, well, what if we have a 3-carbon acid and we mix it with a 4-carbon alcohol under acidic conditions? We get this ester, and we name it the same way. We name the alcohol first, since it's 4 carbons long, a straight chain. It's butanol, but we call it butyl, space, propanoate. Now that is a little, I guess I should comment on that. Where's the O coming from? Well, again, remember that the O is, the parent acid has an O in it, propanoic acid. So we drop the IC ending of the acid. We drop the ic acid part, and we add the ATE suffix to call it a ester. Just another rule to add to your portfolio of rules to name all these compounds. Again, you've got a lot of rules to organize in the next week or so to apply these, but I know you can do it. So this is called butyl propanoate. You always name the alcohol part first. this particular ester smells like apples, but a lot of these esters can, this, to some people it might smell like apples, to some people it might smell like oranges. It's all kind of subjective, but they all have generally pleasant smells. Here's the line drawing of that. Again, you can make a variety of good smelling things to make other esters. Here's how you can make something that smells like pineapples. If you look at this, let's say you knew this is the product you wanted to make, how would you make it? Well, you'd say, well, this part I know has to come from the alcohol, the part I wrote in red. That's 2 carbons long, so I need ethanol, a 2-carbon alcohol. And this part in blue has 1, 2, 3, 4 carbons in it, so I need to use butyric acid. Nasty smelling stuff. It's interesting though, you can take something that smells terrible and something that doesn't smell like anything, and you mix them together for about an hour under acidic conditions and you get ethyl butyrate, which smells like pineapple. So it's strange how our senses detect these chemicals and how we detect smells. But you always get a water molecule spit out. Again, it's coming from this linkage here. You bring this oxygen together with that O, and you make an ester linkage. If you mix acetic acid with 1, 2, 3, 4, 5, 6, 7, 8 octanol, so this is octanol. It's got 8 carbons in it. It's the 1-octanol, and you mix vinegar essentially, but acetic acid. And you mix oxanol, you get octyl from the alcohol part, acetate from the acid part. Smells like oranges. Wintergreen, the smell of breath savers and other mint flavored things, is made a little differently from an aromatic acid. This OH here doesn't take part in the reaction. It just is part of the salicylic acid molecule. This is the acidic part. So this O here pretty much becomes bonded right there, and you get this compound here, methyl from methyl alcohol, salicylate from salicylic acid. Oil of wintergreen. It's another common name for that. So I will want you to understand the naming of esters, and maybe even give you some, I'll give you a couple of reactions on next week's quiz, so make sure you study up on these, and how do we make esters, since this is such a famous reaction, and I think it's something pretty straightforward and easy to, not easy to understand, but it's pretty clear. So I'm going to put a video on in a couple days and just give you some practice. I might go over like a problem set or something to make sure that we can review a little bit more. So I want to just kind of summarize all these reactions and talk about oxidation of organic compounds, because that's really what we've been talking about in these videos that I've put online today, going from alcohols to aldehydes to ketones to carboxylic acids to esters. Those have all involved oxidation and reduction reactions. So let's just review a little bit about and help you understand the chemistry of these reactions a little more, and then we'll talk about our last functional group. So as you know, oxidation involves an element going from a lower oxidation state to a higher oxidation state. It involves a loss of electrons. So in these organic reactions, it's usually carbon that's losing the electrons, and it's giving them to some other element, usually a metal that we haven't discussed that's used to oxidize the carbon. But sometimes it's given to another molecule that contains carbon. And reduction, as you know, is the gain of electrons, usually by carbon. That is, so it means it's carbon's being reduced. So how do we track redox reactions of organic molecules? Well, there's really 2 ways to look at oxidation now, and 2 ways to view reduction. Oxidation in an organic chemistry sense is an increase in the number of bonds to oxygen, or it's a decrease in the number of bonds to hydrogen. What do I mean by that? Well, let me get my models out here and show you. So here is ethanol, and I should have, where is my acetic acid molecule? Hold on, bear with me. Here it is. This is acetic acid. So this is a visual representation of an oxidation. So this is ethanol, CH3CH2OH, and this is acetic acid, CH3 C double bond OH. What's the difference in the molecules? Well, according to my definition I just said, oxidation involves an increase in the number of bonds to oxygen. Well, yes, carbon, this is a carbon-oxygen single bond. This is a carbon-oxygen double bond. So I've increased the number of bonds to oxygen, or a decrease in the number of bonds to hydrogen. That's also going on. Notice here I have a carbon with 2 bonds to hydrogen, and here I have a carbon with no bonds to hydrogen. So I've clearly decreased the number of hydrogens going from here to here. Generally, there isn't a direct step from here to here. Usually I would go from the alcohol to the aldehyde, and then I'd go from the aldehyde to the carboxylic acid. It's usually a sequence of steps. But this is the beginning point, this is the ending point. That's one way to view oxidation in organic chemistry. Reduction would just be the inverse. It would be it's a decrease in the number of bonds to oxygen. So here I have, 3 oxygen bonds. That's a double bond, so it counts for 2. 1, 2, 3 bonds to oxygen. And now I go to a more reduced form of this 2-carbon compound, an alcohol. It only has 1 bond to oxygen, so I've decreased the number of bonds to oxygen. Or I can view it as an increase in the number of bonds to hydrogen. Same thing, same conclusion. I only have 1 hydrogen bond in this part of the molecule, and now I have 3 bonds to hydrogen. 1, 2, 3. So I've increased the number of bonds to hydrogen. So that's a reduction. So reduction, oxidation, left to right, as you see this. So it's pretty much the same sort of reaction that we discussed before with just gaining and losing electrons. So we can kind of summarize what's been going on in all these reactions with just movement of electrons. If you look at carbon, for instance, in methane, and you have to think back a little bit, but when we talked about assigning oxidation numbers, we said that was a way to keep track of electrons in a chemical reaction. It's not a true oxidation, it's not a true electronic charge, it's just a way to look at a counting of electrons, so to speak. So if we take methane, for instance, that's the most reduced form of carbon there is. It's carbon in its lowest oxidation state, which is -4. Well, as we go from a normal alkane to an alcohol, which is the next highest oxidation state, we have to lose 2 electrons. Carbon has to lose 2 electrons, but it also has to gain a bond to oxygen. So that's considered an oxidation. Well, to go from an alcohol to a aldehyde, you have to lose 2 electrons again. It always involves a loss of 2 electrons every time you go between you go to the next higher oxidation state. So from an alcohol to an aldehyde, you lose 2 electrons. From an aldehyde to a carboxylic acid, you lose another 2 electrons and become a slightly higher oxidation state of carbon. And then if you go all the way to burning the organic material to make CO2, you go to the highest oxidation state of carbon, which is this one, when it's doubly bonded to 2 oxygens. That's as far as you can go. But notice every time that you can calculate the oxidation state of carbon. In methane, it's -4. In methanol, the oxidation state of carbon is -2. In formaldehyde, the oxidation state of carbon is 0. And in acetic acid, the oxidation state is +2. And in CO2, it's +4. I'll show you how to do that in a second. Let me just show you why do we care about all this stuff? Well, if you're a biochemist or a doctor or a thing, you have to understand the biochemical applications of this. For instance, the Krebs cycle is an important process that occurs in the body for the production of energy. We just take this for granted because this is happening on millisecond and microsecond timescales in our cells. What we get energy from food because molecules are changing oxidation state. It's just an amazingly complicated process that just gives me a headache when I try to understand it. But to have a detailed understanding of it for most of us, including you, is not necessary. But just have a general idea of what's going on. So how do you tell, for instance, that this molecule to this molecule is being oxidized, or this molecule oxaloacetate to malate is being reduced? How do you tell? Well, if you just look carefully here we have a HCC. Oh, they're all singly bonded in this compound called succinate. These are all electrically charged particles. They are depends on the pH of the cell as well. These are the basic forms of these compounds. But that's not important at this point. What is important is just recognizing an oxidation versus a reduction. When you lose hydrogen, just like I said, one way to view oxidation is an increase in the number of bonds to oxygen, or you can view it as a decrease in the number of bonds to hydrogen. So notice here, going from a saturated compound to an unsaturated compound with a double bond, I've decreased the number of bonds to hydrogen. So that's viewed as an oxidation in organic chemistry. Very important reactions. These are the things going on to, like I said, create energy or to help digest our food, all sorts of processes. This is a reduction. It's the opposite. Here we're going from when you have a carbonyl group going to an alcohol, you can view that as a reduction because that involves a decrease in the number of bonds to oxygen. Here you have two. I'm talking about the decrease in number of bonds to oxygen between carbon and oxygen. So you have two bonds to carbon-oxygen here, and now here you only have one, a single bond. So that's considered a reduction. And also you can view it as it might be easier for you to see that this is a reduction because you're increasing the number of bonds to hydrogen. Here you don't have any bonds to hydrogen in this part, but now you have two. You introduced two hydrogens, one bonded to oxygen that was here, and another to the hydrogen, or to the carbon here that was attached in the carbonyl group. So let me I think it might be useful just to show you where I got these numbers from. Just this will help. This is coming from an early part of the course too. So let's just look at methane, for instance. I don't know if I'll go through all of these. Again, I'm at 22 minutes and 41 seconds here. I don't want to run out of time again, but here is methane. How do we figure out the oxidation state of carbon and methane? Very easy to do. You look at the two atoms involved in a bond. Let's just focus on one bond at a time. And hydrogen, as I've said before, always gets a +1 oxidation number. And the other rule that you might remember from weeks ago is you always give oxygen a -2 oxidation number. So here we have 4 hydrogens, each with a +1. Therefore, since this is a neutral molecule, it has a 0 electric charge, or molecular charge, and the only conclusion you can draw is that carbon would have a -4 oxidation number because -4 plus +4 gives you 0. Go to the next higher oxidation state, an alcohol. So let's just draw the simplest one, methanol, methyl alcohol. Here we go. All right, so how do you figure out the oxidation state? How did I come up with -2 for the oxidation state of that carbon? Same way, give the hydrogens each a +1. Now, oxygen is normally -2, but when it's hydroxide, it's -1. So how do I give you that? Let's see, if I have +1, +1, +1, and a -1, that adds up to +2. To give 0, I need to have -2. So why is oxygen here just -1? That might be a little bit confusing. Well, because the hydrogen that's attached to it has a +1. So I'm talking about the OH as a whole. If you have a -2 here and a +1 here for oxidation numbers, as you would normally assign, you add those up as a whole, since we're considering it as a group attached to a carbon, you get -1. So that's where I came up with this -1 charge there. But again, +3 -3 gives me 0. You keep going, go to the next one, formaldehyde. Here we have this in the next higher oxidation state of carbon. Here we'd have +1 on that one, hydrogen, +1 on that hydrogen. We give oxygen when it's not attached to a hydrogen, we give it a -2. And now notice that the oxidation numbers balance. +2 and -2 cancel to 0, so therefore carbon in an aldehyde has an oxidation number of 0. But notice every time I'm going to the next higher oxidation state, I'm losing 2 electrons. So you go to the carboxylic acid, you get how to come up with +2 for the oxidation number of carbon in that compound. Well, now we give this group a -1. So again, the group itself is -1, and then we have a -2 here. So what does that add up to? -2 -1 is -3. I need a +3 to balance that out. So therefore, that would mean that that has to be a +2. +3 -3 I'm always trying to add up to 0. And then finally, all the way up to CO2, I have a -2 oxidation number there, -2 oxidation number there. Therefore, carbon in its highest oxidation number is +4. And notice in going all the way from the most reduced state of carbon in a alkane to the highest oxidation number is involved a loss of 8 electrons. So that's really all chemistry is. Now that we're kind of wrapping up this course, chemistry is just a matter of the electrons being transferred between atoms. That's really what it breaks down to on the simplest level. It's just movement of electrons from place to place. So I have one more group I want to comment on, and then I want to show you, just kind of review a little bit here. We're at 27 minutes, so I will go through this rather quickly, and I probably have to do another video. Sorry, because I'm running to my time limit with this one. I'm sorry, I tend to ramble on too much sometimes. But the last compound that's important is amines. There's really another one called amides, but that's getting too far into this. We don't need to worry about that. Amides, which is replace this with a D. Amides are a class of compounds found in proteins, which are obviously important things to know about. But right now, let's just end it here with amines. These are nitrogen-containing compounds. They have carbon in them, obviously, but the main functional group is a nitrogen atom. So they all derive from ammonia, which is NH3. It's a gas. And you can have 3 types of amines. You can have an amine that has 1 carbon on it, which we call a primary. You can have an amine that has 2 carbon groups attached. That's a secondary, called a secondary amine. And you can have a tertiary amine. Notice how we classify primary, secondary, and tertiary for amines is slightly different than how we classified primary, secondary, and tertiary for alcohols. If you recall, a primary alcohol is something like this, where you have CH3, CH2OH. That's a primary alcohol because the OH is attached to a carbon that only has 1 carbon attached to it. It's at the end of a chain. A secondary alcohol would be something like this, where you have a CH3, C, and then you have an OH, and this might be bonded to another CH3 up here, but then a hydrogen there. So this is a secondary alcohol because the OH is attached to a carbon with 2 groups. And a tertiary alcohol would be like T-butyl alcohol, where the OH is attached to a carbon that's attached to 3 carbons, so that's a tertiary. Well, amines are classified according to just how many carbon groups are attached directly to the nitrogen. It's a little different. So 1 carbon attached is primary, 2 carbons attached is secondary, 3 carbons attached is tertiary. But they're all weak bases. They're weak bases because nitrogen has a lone pair of electrons on it, and therefore it's seeking out protons. I'm at 30 minutes here, so if this video ends abruptly, I apologize, and I will continue on in the next video. But I'll just keep going here until it cuts me off. It's giving me the thing that symbol that I'm almost reached my limit, so I'll end this video right here. I apologize, didn't quite finish. The next video will be somewhat short, but I will I'll re-emphasize all this, and then we will wrap things up in video number whatever that is, 5.